How will China's latest hardware change aerial warfare? Radars use radio waves to determine the range, angle, or velocity of objects.
Well, stealth is a critical capability of modern military equipments. To go invisible on enemy radar provides a significant advantage in the battlefield.
Quantum radar, which could make even the stealthiest aircraft lose its most potent capability.
China has tested a breakthrough drone-mounted quantum sensor that could reveal what's long been hidden beneath the ocean's surface, submarines. This device detects tiny magnetic ripples that even advanced stealth designs can't fully hide. With successful real-world trials showing extreme accuracy, the technology could redefine how undersea activity is monitored. In this video, we'll explore how the system works, the impact it could have on global naval operations, and the challenges that still stand in its way. China's latest quantum detection trial took place off the coast of Weihai, where researchers mounted a coherent population trapping (CPT) atomic magnetometer on a specialized drone. This instrument works by measuring how rubidium atoms shift between energy states when exposed to magnetic fields, producing resonance signals that can be precisely recorded. These measurements can detect changes in magnetic strength far too small for conventional systems. The device's performance in testing was remarkable. Initial readings achieved a precision of 2.517 nanotesla (nt), already highly sensitive, but after post-processing corrections, the accuracy improved to 0.849 nt. To put that into perspective, that's over 1 billion times weaker than the pull of a typical refrigerator magnet. Even more impressive, repeated passes over the same area produced a 99.8% match in readings, confirming its stability and reliability. The drone was tethered to reduce interference from its electronics. A fluxgate magnetometer was integrated to filter out environmental noise. Ground-based stations synchronized with the drone's GPS were used to further clean up data, ensuring that the anomalies detected were genuine. The testing grid covered an area of 400 meters by 300 meters, allowing researchers to track the faint magnetic wake that submarines can leave behind as they move through seawater. Traditional magnetic anomaly detection (MAD) systems, often carried by aircraft, have limits in both range and sensitivity. They are also less effective in regions like the South China Sea, where Earth's magnetic field runs nearly parallel to the surface, creating blind zones. The CPT magnetometer overcomes this challenge, allowing it to detect magnetic changes even in such difficult conditions. What makes this breakthrough so significant is its adaptability. Drones equipped with these sensors could operate in coordinated networks, scanning vast areas quietly and persistently. Instead of relying on large, noisy aircraft, a fleet of small aerial vehicles could work in shifts, maintaining continuous coverage of strategic areas. This quantum-driven approach doesn't just enhance detection. It fundamentally changes how monitoring can be conducted in shallow coastal regions and potentially in deeper waters with future refinements. By turning faint, invisible magnetic traces into visible maps, this technology takes a decisive step toward a new era of undersea awareness, one that could transform the way the ocean's hidden activity is understood and tracked. The successful testing of this quantum magnetic detection system could influence how submarine operations are planned and conducted worldwide. Stealth has always been the defining feature of submarines, allowing them to operate undetected for long durations. This invisibility is especially critical for nuclear-powered submarines, which perform long-range patrols and can remain submerged for months. If such drones can consistently identify the faint magnetic anomalies left by submarines, they could become part of a much larger detection network. By deploying multiple drones along strategic maritime routes, it would be possible to create a moving net of sensors that monitor activity without requiring large ships or constant human oversight. Strategically, this matters in regions where control over sea lanes and choke points is important. Maritime areas such as the South China Sea, the Taiwan Strait, or the approaches to major ports could be monitored more effectively, making it harder for submarines to operate unnoticed in those areas. identify patterns that match known submarine signatures, and eliminate false positives caused by natural magnetic fluctuations or civilian vessels. This means that future detection systems may not only be more sensitive, but also more accurate and automated. However, it's important to note that even with high sensitivity, open ocean detection remains more challenging than monitoring confined coastal waters. Submarines operating in deep waters produce smaller and more dispersed magnetic signatures and eliminate false positives caused by natural magnetic fluctuations or civilian vessels. Nevertheless, for operations near coastlines, shipping lanes, or in areas with complex seabed topography, the quantum detection approach could prove highly effective. From a technological standpoint, the modularity of drone-based systems is a major advantage. Drones can be deployed quickly, repositioned as needed, and upgraded with improved sensors without requiring new large-scale platforms. This flexibility means the technology could be scaled incrementally, starting with regional coverage and expanding over time. In essence, the leap forward in quantum magnetic sensing is more than a scientific milestone. It's a potential rethinking of how the underwater domain is monitored, moving toward a future where stealth may no longer guarantee invisibility in certain areas. While the results from the Weihai trials are impressive, there are still significant hurdles before such systems can be used for large-scale ocean monitoring. The first challenge is environmental noise. Earth's magnetic field is influenced by multiple factors: solar activity, ocean currents, and local geological variations. While ground stations and advanced filtering can reduce interference, operating in turbulent conditions or across varying latitudes presents new calibration challenges. Another limitation is the coverage area. The 400 by 300 meter grid map during the trial is a promising start, but it's far smaller than the vast patrol zones submarines traverse. Scaling up would require either larger drones with extended range or a coordinated network of many smaller drones working together. This adds logistical complexity, as well as the need for robust communication links between units. Durability and reliability are also key concerns. Maritime drones must operate in environments with saltwater corrosion, high humidity, and variable weather conditions. Ensuring that delicate quantum sensors remain stable and accurate under such stress will be essential for real-world deployment. Additionally, there's the factor of data processing speed. While AI can enhance detection accuracy, processing large volumes of magnetic data in real time is demanding. Systems must not only detect anomalies, but also classify them correctly without slowing down the monitoring process. Submarine operators are not without countermeasures. Techniques such as degaussing, reducing or eliminating a vessel's magnetic field, have been used for decades. Advances in non-magnetic materials and hull coatings can also help reduce detectability. Future stealth designs may integrate active systems that generate counterfields to mask a submarine's signature. Still, these countermeasures require constant refinement, especially as detection systems grow more sensitive. The dynamic between detection technology and stealth measures is cyclical. Advances in one drive improvements in the other. The introduction of drone-mounted quantum sensors adds a powerful new tool to the detection side of that cycle. Looking ahead, this technology could evolve beyond drones. Fixed seabed arrays, ship-mounted platforms, or even satellite-linked buoy networks might one day carry quantum magnetometers, creating multi-layered detection grids. The path forward will involve balancing technical feasibility, deployment cost, and the speed at which improvements can be made. The Weihai trials show that the core concept works. The question now is how quickly it can move from a controlled demonstration to an operational system capable of persistent, wide-area coverage, potentially reshaping the understanding of what can and cannot remain hidden beneath the waves. China's drone-mounted quantum magnetometer has moved submarine detection from theory to reality, delivering precision never before achieved in real-world trials. While its reach is currently limited and environmental factors remain a challenge, the technology's potential to reshape how undersea activity is monitored is undeniable. From coastal surveillance to strategic choke point monitoring, it opens new possibilities for continuous, unmanned coverage. The future will depend on scaling, refining, and integrating this system into broader detection networks, while countermeasures evolve in response. One thing is certain: the oceans are becoming more transparent, and the boundaries of stealth are being tested like never before.